Similar to the continuous time case, we do have the properties for the discrete time Fourier transform as well. The first property is the property of linearity. As most of these properties are similar to what we have seen for the continuous time Fourier transform, I'm not going to derive each of them, as most of them are similar to what we have seen it already and we have derived them. So I'll simply run through all these properties quickly. So the first property is the property of linearity. The linearity property says that if we have a signal x of n, x1 of n, whose discrete time Fourier transform representation is given by, so it is discrete time Fourier transform dtft is given by, say, x1 of omega, and let's suppose if I have another signal x2 of n whose Fourier representation dtft discrete time Fourier transform is given by x2 of omega. If we take a linear combination of this x1 of n and x2 of n, so let it be a times x1 of n plus b times x2 of n, we are going to get the similar kind of expressions in the Fourier domain as well. So the dtft is going to be the linear combination of their individual Fourier transforms. So a times x1 of omega plus b times x2 of omega. So here, if we have a linear combination of two signals, their Fourier transforms are going to also have the linear combination with the same scaling factor of a and b as we have in the time domain. So this property is called as the linearity property. Next is the property of time shift. The time shift property says that if we have a signal x of n whose Fourier transform, the discrete time Fourier transform, is given by x of omega, then the Fourier transform of shifted version of this signal, say n minus n naught, is going to be the same x of omega but being scaled by a factor of e power j omega. That's going to be scaled by a factor of e power minus j omega n naught, where this n naught is the amount of shift. Now this property is called as time shift property. As we have this property for time shift, we do have the property for the frequency shift as well. So third property is the frequency shifting property. Frequency shift. This property says that if we have a signal whose Fourier transform is x of omega, then let's suppose if we shift this signal in the Fourier domain by an amount of omega naught, we are going to get a similar signal. So in this equivalent signal is going to be x of n, but with a scaling factor of e power j omega naught n, where this omega naught is the amount of shift in the Fourier domain. So you can see a close relation between this time shift and the frequency shift property. If we shift a signal in time domain, there's going to be an exponential factor. In the frequency domain, if we shift the signal in the Fourier domain, there's going to be an exponential factor in the time domain. Of course, with a change of sign here due to the expressions, the analysis and synthesis expression differ in this negative sign. So there's a difference in the sign itself, and of course the shift of omega naught here and a shift of n naught there. Next property, And with this Fourier shift, the frequency shift property we have already seen when we were trying to derive the Fourier transform, the discrete time Fourier transform for the periodic signal in the previous module. If you recall, we have taken a shifted version of the impulses and we have come up with the expression for the discrete time Fourier series in a similar way. So that you can consider as a proof for this Fourier shift property for the specific example of this impulses, the shift impulses that we have already seen in the previous module. Next property is the property of time reversal. The time reversal property says that if we have a signal whose Fourier transform is x of omega, so the discrete time Fourier transform is x of omega, then the time reverse version of the signal x of n is going to give you the discrete time Fourier as the x of minus omega. So reversal in time is going to give you reversal in the frequency. Another property the fifth property is the property of convolution. Convolution. So this property says that let's suppose if you have a signal x of n whose discrete time Fourier transform is given by x1 of omega, and let's suppose if you have another signal x2 of n whose discrete time Fourier transform is given by x2 of omega, then the convolution, if we have a convolution in time domain, x1 of n being convolved with x2 of n, the resultant signal in the Fourier domain is going to be multiplication of the individual Fourier transforms. It's going to be x1 of omega times x2 of omega. This is similar to the property that we have seen for the continuous time case. If you have a convolution in time domain, we are going to get a multiplication in the Fourier domain, the frequency domain. Next property is the property of multiplication. So let's say if we have a signal x1 of n, again whose Fourier transform is given by x1 of omega. So if an x2 of n whose Fourier transform is given by x2 of omega, and let's suppose if we multiply these two signals in time domain, so x1 of n multiplied by x2 of n is going to have the Fourier transform as the convolution of the individual Fourier transforms. So this is going to be x of omega so the expression is going to be 1 upon 2 pi integration over a period of 2 pi x1 of omega dash x2 of omega minus omega dash d omega dash. You can see that this expression is similar to the expression for convolution, and of course there is a scaling factor of 1 upon 2 pi there, but this is equivalent to x of tau h of t minus tau. So there is a convolution in the Fourier domain, but again the convolution is over a period of 2 pi, so this can be considered as a periodic convolution of the convolution within a period of 2 pi. So there is a close relationship between this convolution and the multiplication property. We can see that if we convolve in time, we are going to get a multiplication in the frequency domain, and if we multiply in time, we are going to get the convolution in the frequency domain. So this is equivalent to, this equals to x1 of omega and convolved with, so there's a circular convolution with x2 of omega, and that is being scaled by a factor of 2 pi. Next property, is the conjugation property, which says that if you have a signal x of n whose dtft is given by the discrete time Fourier transform is given by x of omega, then the conjugate of this signal x of n will give you the discrete time Fourier transform as x of conjugate of omega minus omega. So this is a property of convolution. Similarly, there are various other properties. So let's have another property, in fact a theorem, that is the important theorem called as Parsevals theorem. This Parsevals theorem we have already seen for the continuous time Fourier series and transform. Let's look at this Parsevals theorem. For this discrete time Fourier transform. The Parsevals theorem says that if you have a signal x of n, any discrete time signal, and if we calculate its energy, so we are calculating the energy, so we'll take a mod, take a square and sum it over entire range of n from minus infinite to infinite. So if we take energy of this signal, the energy is going to be retained in the Fourier domain. So this is going to be equals to 1 upon 2 pi integration over a period of 2 pi mod of x of omega square d omega. So what this means is the energy in the time and the Fourier domain remains constant. So if you have an energy in time domain, that is going to be equals to the energy in the Fourier domain. So x of omega, the Fourier series coefficient, Fourier transform coefficients, if you take a square of those coefficient, mod of them, and then square them, take an integration over limit of 2 pi, and that is being scaled by a factor of 2 pi, we are going to be getting the same value as that of the energy in the time domain. This is called as the Parsevals theorem. Let's stop here.